Back. In this video, we are going to solve example 8.7 that is taken from chapter number 8, Combined Loading, and book name is Mechanics of Material by R.C. Hibbeler, 9th edition. So statement is a rectangular block has a negligible weight and is subjected to vertical force P in figure A-8A. In part A, you have to determine the range value for the eccentricity EY of the load along the y-axis so that it does not cause any tensile stress in the block. And in part B, specify the region on the cross section where P may be applied without causing a tensile stress in the block. So you can see this is a rectangular block. This height is H and this width is B. This is y-axis, this is x-axis, and this is z-axis where we have a P load in the direction of z, and that is eccentricity away from this center. Our x-axis is EY. So due to this load and eccentricity, you will see that there will be a compressive stress along with the bending moment. So you have to find this, how much we should locate this EY so that it does not create any tensile stress in this block. Usually tensile stress will occur at this region. I will show you, and then you have to specify the region. So let's start with the solution. So what will be the first step is that if you move this point P load to the center or centroid, so definitely you can see you can move it, but that is away from this centroid at a distance of EY. So if you want to move this load to this point, so definitely you will be having a moment M that will be clockwise, and this moment will be equal to P into EY. Clear? So we will do it. We will move this load in this Y, in this Z direction. Let me choose another color. So let this load is downward, that is equal to P, and you will be having a clockwise movement in this direction M. So this P will be equal to, that is given, not given, okay. So this P is load and this moment M will be equal to P multiplied by EY. Clear? And that will be clockwise movement. Now you can see this is the combined loading where you have P load that is compressive. So due to this P load, we have stress is equal to minus P divided by A, and due to this movement we will have bending stress that will be equal to minus M into Y divided by I. So if you put the value of M, so you will get minus P times EY into Y divided by I. So total load or stress will be equal to minus P divided by A minus P into EY into Y divided by I. Now, what if you see that if you take positive EY direction, if you take this EY in positive Y direction, you can see this is positive Y axis, and if you take Y positive, so due to this movement, this beam will bend like this. So this portion will be in compression and this portion may be in, or it will be in tension due to this bending movement. So if you take positive Y direction, so this will cause compression, and if you take this Y as negative in negative direction, so this portion will be in tension. So I have this equation. Now if you take minus P divided by A as common, so minus P divided by A is common, so we will have only 1 over here, and we will have EY into Y multiplied by A divided by I. Okay, and this I will be I about x-axis. Okay, I about x-axis, because you can see the movement is about x-axis, so movement of inertia of this cross section should be about x-axis. Now we have this equation. The total stress will be equal to minus P divided by A into 1 minus, this is minus, so this will be plus. So it will be plus A into EY into Y divided by IX. Okay. Now what, as we have seen that due to this movement, this only due to this moment this portion will be in tension, and this due to this load P, this whole section will be in compression. Clear? So what if I want to have this y is equal to negative minus h by 2. Minus h by 2 will be this at this. So if I take y is equal to minus h by 2, so it will put the value of y. For y is equal to minus h by 2. So we will have this stress will be equal to minus P divided by A into 1 plus this A will be there, EY will be also there, and y will be minus h divided by 2 into Ix. So if I simplify it, this equation will be equal to minus P divided by A into 1 minus A into EY h over 2Ix. If you can see that if you multiply it with this will cause compression, and if you multiply it with this it will be positive, so mean there will be a tensile stress at this point. If you see that if you want compressive stress for this equation, so this equation will be negative if 1 minus A into EY multiplied by h divided by 2Ix is a positive number, and this will happen when this 1 should be greater than 1 is greater than AEY h divided by 2Ix. I will repeat that this equation will be negative, still remain negative, if this 1 minus A into EY h divided by 2Ix value is positive. And you can see that it will be positive for 1 is greater than A into EY over h. Now what is A? So A is the cross-sectional area of this rectangular section. You can see its height is h and breadth is b. So A will be equal to b multiplied by h. And what is Ix? So moment of inertia about y-axis. So x-axis. So this is x-axis, this is height, and this is breadth. So bh cube over 12. So I can write 1 over 12 bh cube. So put it in this formula. 1 is greater than b multiplied by h into ey into h divided by 2 multiplied by 1 over 12 bh cube. So what we will get is 1 is greater than 6ey over h, or you can see ey is less than 1 over 6h. I will write ey is less than 1 over 6 into h. So this is ey when h is taken as minus h by 2. For y, if you put y is equal to h by 2 in this equation, so what you will get ey will be greater or equal to minus h over 6. So this is the range for ey should be less or equal to 1 over 6h, which we get from here, and ey is greater or equal to minus 1 over 6h. So if you put ey distance in this range for this load P, if either you move it toward positive or negative side. Clear? So if this is the range for ey is 1 over 6. For example, I will put, let this point is G and this point is F. So this is the range. For example, this distance is minus 1 over 6h and this distance is plus 1 over 6h. So 1 over 6h. So moving this load P in between these 2 points, there will be no tensile stress in this block. What about this width B? So note that there is this is sometimes referred as middle hand rule. I will write from middle third rule. What does it say? It say that it is very important to keep this rule in mind when loading columns of arches having a rectangular cross section and made of material such as stone or concrete, because they are good in compression and do not require tension, which support little or no tensile stress. Hence, we extend this analysis in the same way by placing the P along x-axis. The result will produce a shaded parallelogram. So what it means that if this is h by 6 and h by 6, similarly along this x-axis you can put b by 6, b by 6. So if I put this value, let this point is your point E and this point is your point H. So you can see you will have a parallelogram. So it means that this is the region. This parallelogram is the region where when this load, it can be here, it can be here, it can be here, it can be here, it can be anywhere within this parallelogram region. So when you applied this load P, it will not produce any tensile stress in this block. And this was all about this example 8.7. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching.